In the previous video, we started talking about the examples part of our discussion on quantum mechanics. Let's now move to part 2 of the examples. In this video, we'll take a look at two more examples or problems. So example 4, you have a wave function of a particle with mass m is given by the following. Psi of x is equal to a cosine alpha x, where negative pi over 2 alpha is equal to or is less than or equal to x, is less than or is greater than or equal to is where x is less than or equal to plus pi over 2 alpha. So x ranges from negative pi over 2 alpha to plus pi over 2 alpha. Any other location, any other value of x, y of x is 0. Lambda is, alpha rather is 1 times 10 to the 10th power per meter. Find the normalization constant A. So find capital A. The probability of finding any particle when you look anywhere from negative infinity to positive infinity is of course 1, as we have previously mentioned, as we have repeatedly mentioned before. The integral from negative infinity to positive infinity of the probability density square of absolute value of psi dx is equal to 100%. The same goes if we limit the range for the given range. If we limit x to be from negative pi over 2 alpha to positive pi over 2 alpha only, the probability of finding the particle is also 100%, since psi is 0 anywhere else. Psi of 0 for that range is a cosine alpha x. So get the absolute value of that and square it. A is constant. So a squared, we can bring it out of the integration. We are just integrating cosine squared of alpha x dx, and the whole left side is equal to 1. Integrating and then integrating from negative pi over 2 alpha to pi over 2 alpha, we get a squared times pi over 2 alpha is equal to 1. Isolating, we are able to get a to be square root of 2 alpha over pi, or 7.98 times 10 to the 4th power square root of radians per meter. Next, we have the following example. Example 5. Suppose a proton is confined in a box of width L, 1 times 10 to the negative 14 meters. So instead of an electron, this time we have a proton, and it's confined to move only within this region, box of width L. If the proton is in the first excited state and it emits a photon, so in effect it loses an energy equivalent to the energy of the photon, the proton transitions from excited to state to the ground state, meaning the energy loss of the proton is from excited state to ground state. What are the energy and frequency of the emitted photon? So mass of the proton we know to be 1.76 times 10 to the negative 27 kilograms. Length L is given 1 times 10 to the negative 14 meters. The energy for a particle confined in a box is given by En is equal to n squared pi squared h bar squared over 2m L squared. Initially, the proton is in the first excited state, so that's n is equal to 2. Using n is equal to 2, we know m, we know L, all the other values are constants. We are able to calculate the first excited state energy, E2, 1.247269,205 times 10 to the negative 12 joules. Also, ground state energy, N is equal to 1, we can calculate E1, 3.1181737071 times 10 to the negative 13 joules. So ground state energy E1, first excited state energy E2, the difference will be the energy of the photon. The proton goes from E2 to E1. The difference between the two energy levels will be the energy of the emitted photon. Knowing E1, knowing E2, we are able to calculate the energy of the photon. 9.355 times 10 to the negative 13 joules. The energy of a photon is given by the following equation, HF. Knowing energy of the photon, simply divide the energy of the photon by h. We are able to get the frequency of the emitted photon, 1.412 times 10 to the 21 power hertz. And that's it for now. That's it for our discussion on quantum mechanics. Thank you for watching.